Okay, hey, Nancy Nasser again. So we're in chapter 8, and chapter 8 is all about causal discovery and causal inference. And this is one of the chapters where I usually try to tread very, very carefully. In my class, I cover a few things for main concepts, main ideas. I tend to have a lot of undergrads in my classes, so causal inference and discovery may be a little bit of an overkill for them. I do have the um, grad version of my class as well. So we have grad students there, and there I get to be a little bit more flexible because we can cover a little bit more about whether discovery there and inference. And this is what we're going to be doing today. So we're going to start with I'm going to treat this to be very, very upfront, like an undergrad lecture. And we'll go from there. We'll go from there. So as we all know, if you remember that pyramid thing we had in chapter 2 or chapter 3, we start with a black box model, gray box, white box, gray box, and then causal model. So we're at the very, very tip of that pyramid right there. And causality and causal inference is actually starts, turn this off first. It stems from, it's a very, very old notion. We always would like to know what causes what. And there's this by Da Vinci. He says there is no result in nature without a cause. Understand the cause, and you will have no need for the experiments. So it's, as you can see, if you know why, then that we actually solve the problem if we know why and how. So basically, we may not need to do as many experiments as we would like to otherwise, because we know what something happens. We don't have to really reinvent the wheel every time we think about it. So in this chapter really stems from the fundamental idea for engineers is we would like to know, how things happen to be and why they happen to be. And the process is, as always, we try to simplify. The process is very simple. We do experiments. Say we have an experiment. We try to test something. And the main reason from the test is to observe some response. And the response is something that we're interested in. For instance, how do beams deflect, or how does fire affect concrete or steel, or what about, creep in timber, all those different types of things. So what we do is we have an experiment and we usually manipulate something. We have the beam a little bit larger, different material, different loading setup, different boundary conditions, and we observe. And this observation is from ML, we call it data. And the same thing with the observation is something now we can see. And if we see something, the more we see different things from it, becomes a little bit easier for us to put things down into a model. So manipulation, then we have observations. And once we have those observations, we can come back and we can say, okay, well, now let's try to figure out something. And this something is what we're going to call model. And what our goal is to predict something. Okay, very, very simple. Now, when it comes to ML, remember everything before this chapter was all about data. So how can we get how and why from data? This is where we're going to have to use a different approach now. So to start with, we think about experiments, just like what we mentioned. And the goal from the experiment, other than observing something, is really we're trying to uncover DGB. And DGB stands for data generating process. We would like to know how this thing happens and why. And once we know the DGB, this becomes very, very strong, very, very important for us, because now we can create a model that can mimic the DGB. It's no longer an empirical model that we can just see it, or we get data by observations and we come up with like a best fit equation or something. No, this is a different type of model. This model goes down and says, okay, well, this is the relationship between the parameter because we know how these things work together, right? And whenever you start to use terms like DGB, causal inference, causal discovery, this is where we're going to have to use something similar. And this is where we go and graduate to start to think about a causal path, or a cause. This is an effect. And this is here leads to or causes an effect. So we have some causes, leads to effect. Anything more than this is really going to be a bit complex, because there is also the philosophy of causes to effects or effects to causes, which is very fascinating. But we can always talk about those for a different recording. Okay. So in our test, the very first specimen is a benchmark, as we all know. We're just trying to see the simplest of behaviors. And then other specimens, we try to manipulate them by changing one thing at a time or two things at a time, hopefully one thing at a time, because changing more than two or three becomes a little bit hard to quantify how much this one contributes to this observation we see. Okay, good. So we have specimens, benchmark, manipulated ones. We have a phenomenon, let's call it X, and we'll go from there. So hopefully this is smooth so far. We're going back all the way to the very basic fundamental. Now, let's see that the experiment we have is, I'm trying to see the bending moment of this much to beam A. And then I apply this much force, this much moment, I see beam A fails. Here's what we're gonna have to think. Well, the first question is, why did this beam fail at 361.6? Like, why didn't it fail at 361 or 350 or 400 by 361.6? We would like to figure out, well, was this failure triggered by the geometry of the beam or by the material properties of this beam? Which one was the cause? We know that if we multiply them, we're going to have moment capacity, but which one is really the one that causes failure? We're going to start thinking about, well, maybe it's not really geometry or boundary or material properties. Maybe there is something else. Maybe it's boundary conditions, loading configurations, maybe all sorts of things. All of these things are what we call causal questions because we're asking why. Why now? Now, another way to ask these questions is by saying the following. You know, would beam A have failed if it wasn't for the applied loadings? Maybe because I applied loads on the beam has failed. Maybe without applying the loads, the beam will just always sit still and it's not gonna collapse. So is it the loadings? Is it the geometry, material properties? What is it? Now let's say that this beam is made from a different section. Let's say it's I don't know, 18 by 40, grade 36 steel, structural steel. Would this beam still fail at 361.6 or not? So is it like the shape of the beam? Is it the plastic modulus of the beam? Is it the depth of the beam? What is it? Now all of these again are causal questions. So far we haven't asked something like this before because the questions we had before was mainly on prediction. How can we predict this? Or what are the parameters that most influence the prediction? In this case, we're trying to understand the phenomenon. So understanding is a little bit different than prediction. So if we simplify, again, we have the famous equation Z over Z times Fy. Well, what causes the failure of beam A? Well, the effect of bending. If the beam wasn't exposed to bending, then probably we don't have collapse because there's no applied loads. Now, was the failure triggered by the geometry or the properties? Well, in this case, if you look at equation one, let's zoom in a little bit, we see that we have Z times Fy. It's not it's not 0.5 Z times 1.5 Fy. It's both of them are 1-to-1. So it seems like it's an equal relationship there. Now, would beam one fail without the loading? Well, if there is no loading, then the beam will not have any moment capacity, any moment stresses, bending stresses. Maybe it will not have failed, right? So would this beam fail if it was a different section? Well, if it was a different section, then we're going to have to figure out what the applied loads are for that particular section, what the material properties for that section, and figure out if their effects would be less than the applied loading. So in a way here, it seems like everything comes back to applied loading. This is also, of course, one way to look at the problem. One very, very simple way to look at the problem. Let's continue. So this brings us to the following, to causality. And causality is a very interesting / complex topic. And it has a lot of philosophy into it, and this is probably why we don't see it much in engineering. But the notion is the following. The notion is, or at least in the next few slides, my idea was to go a little bit back in time to see how different people view causality, and then from there it might be a little bit easier for us to see how do we define it as engineers. So always go back a little bit in time, see what has been done there, and then come back. Come back and see how this relates to your domain of specialty. So we have Hume, of course, very famous philosopher. And if you read what he says, it's a philosophical relationship. So this is like the very beginning of and a natural relation. So we have two things. So there's going to be a little bit of philosophy between the relationships, and it's natural. So if an object precedes and continues contingents on another, where all the objects resemble the former are placed in a relationship-like residency, and then everything will behave similarly. If you would like to simplify it a little bit, this would be something like the following. Well, a cause to be an object followed by another, where if the first object had not been, the second had never existed. This is very important. You can see there is a negative tone there, had not. Whenever somebody says, if I hadn't done this, I would have done that, right? So this is where you're trying to counterfact what we're trying to say. And this is also where counterfactuals come into place. Counterfactuals is something like, well, if it wasn't for me studying last time for the exam, I wouldn't have passed. So you already have a notion of something that causes something else. If you think about Lewis, Lewis is a different philosopher, and of course, there is a number of philosophers that go over causality. I'm just really showing Hume and Lewis here. Lewis says, well, you can think of a cause as something that makes a difference, and the difference it makes must be a difference from what would have happened without it. Had it been absent, its effect, or some of them at least, and usually all, would have been absent as well. So if it wasn't for the particular thing, nothing else would have triggered. Think of loading. If it wasn't for the loading, it wouldn't have the collapse. Somebody would say, well, what if we have loading, but we change the boundary conditions? Well, this is now manipulation because you varied the boundary conditions. So now, instead of loading, we're thinking about the boundary conditions. So you can take these definitions and really think them a little bit from a different perspective. The goal is not to identify a definition. The goal is really just to look through these and see how do they relate to how we define things in engineering. So evidently, at least for the sake of discussion, we're just saying, because I don't want this to drag for a number of slides. Let's just say that because we applied loads on beam A, the beam has failed. So let's identify the application of loads as a cause. The effect would be the failure. Of course, something else, if you would like to have another example, let's say that somebody's driving on I-85 and there's a car crash, and they were late, and then they would say, you know what, if it wasn't for the car crash, traffic would haven't been delayed. This is another causal observation, but in this case, it's a little bit of a counterfactual as well, because we have the negative. So if it hadn't been X, we would have been, Y. So how do we establish causality? In general, we really have to, we have a number of approaches, but mainly two that we always stick with. Maybe always is not the right term. I try to avoid saying always. We have two, and we see them a lot. We see them much more often. So we have the potential outcome approach, and we have the DAG approach, or the directed acyclic graph approach. Potential outcome tries to estimate population level causal effects. So if you have a population and you're trying to estimate their causal effects, PO is usually the one that we go for. And the math is very, very simple. The average causal effect, ACT, is the response you see minus the response that you don't see. For instance, if you have a beam with steel and the beam fails at 100, then the average causal effect of a group of beams like this would be what we saw, take out or minus a group of other beams that are similar but don't have steel in them. Very, very simple. So if you think about, you see this a lot in like in medical trials. You have a group of people, you give them like medicine or a drug, you have another group, you give them placebo. The average causal effect is the ones that have taken the drug minus the ones that have been taking the placebo. This is how you see if this thing works out or not. Very, very simple. DAG is also comes back to the same approach. However, it's much more visual. And this is perhaps why I'm a little bit associated with it. So DAG is we have graphical methods, and we'll try to identify links. Links are these links or arrows, and an arrow means the item before the arrow causes the item after the arrow, cause and effect. And DAG starts from association, And association, this is purely statistical relationships. So we see things all the time. Then we have intervention. This is us in the lab or manipulating specimens to test them. And of course, we have counterfactual. A little bit hard to examine. And this would say, well, what would have happened if a parameter or more has been altered? Sorry. So association, purely statistics, purely data-driven in a way. Intervention, things we change. Counterfactual is things we can imagine, right? And we've seen this example before. I hope you remember. This is when we have the PhD students plotted against the number of failed bridges. And we're saying here, despite the high correlation, almost 85%, there is really no causal effect here. Because first of all, correlation does not imply causation. So if two things are correlated, that doesn't mean that they cause each other. It could be many, many things that cause both of them or one of them, or there could be some form of causal relationship there. However, it doesn't always mean that there's going to be causation. And the second thing, of course, is we only have a few data where the real data is much, much massive. So we can't really look at the small window and assume that everything else is constant. Just like here. If you look here, you see that the correlation is now is much, much more weaker. Much weaker. So when we think about DAGs, well, statistical associations is something that's easy. For instance, think of this example. If you have an uncoated metallic beam, our experience tells us that it's going to corrode with time. So if you're an engineer and you happen to be monitoring or inspecting different steel beams or metallic beams, you can easily associate, well, this beam has been out there for like 5 years, so I'm expecting to have, I don't know, quarter of an inch corrosion or like, some form of corrosion because and you can easily associate the corrosion level with the time because the more you've seen, the more you can tell. Well, for this flange thickness or for this W shape, this is the expected corrosion with time. Intervention is a little bit different. Intervention says the following. What will happen to the metallic beam if we change one or more of its parameters? So take the same beam, the same identical beam, and coat it now. Earlier, it was uncoated. Now let's coat it. And let's see what's going to happen. Now, because you're adding a layer of coating, you're manipulating the beam. Funny thing is, you can't really test this beam anymore because this beam has already been tested when it's uncoated. So you can't take the same beam, coat it, and retest it. So what we do is we're going to have beam A, and then we're going to go for beam B. We have two beams, and we try those, right? One is going to be observation. The second is going to be with intervention. This is where we chain the beams. In our tests in the lab, it's all about interventions, manipulations. We have one benchmark, we have other beams that come into play. And then, of course, we have counterfactuals. Now, counterfactuals is a little bit, let's read this. What would have happened to the same, let's say, level of corrosion of the same metallic beam after 10 years of exposure had this particular beam, this same beam, been fabricated from a different metal? Okay, so here we're going to have to pause a little bit. So we take the same beam, same identical beam, and we're asking how much corrosion it would have if it had been made from a different metal. Well, we don't have that beam. So we're going to have to manufacture a new beam. And this is why counterfactuals are a little bit, interesting, complex. Same thing with machine learning. For instance, how would the machine learning model answer counterfactual question or even an interventional question if it doesn't have the data? Because it only answers from the data it sees, right? So if you're asking questions from outside the pool of data that you haven't seen with different mechanisms, because metal B is going to behave differently than metal A, so you have a different mechanism there. So it becomes a big, big problem. So using ML for answering these things becomes a little bit tricky. So we can't use traditional ML. We have to use different form, causal ML. So evidently, we're going to think about the following. Well, a causal discovery is we're trying to discover the underlying structure, not for the data, for the causal relations of a DGB. If you remember, under unsupervised learning is that we're trying to uncover the underlying structure of the data. Here, we're trying to understand and specifically discover the underlying structure of the DGB. For instance, how does this parameter relates to this parameter, to this, to this? What is this form of causal relationship? Once you have a causal model or a causal relationship or a DGB or a DAG, then we can use it to infer or predict what would have happened. So the first case is always discover. Second case is always going to be inference because we have it, so we can now use it to predict. So you can think of this as a like a much more advanced equation or a model that can give us, that can answer these questions, counterfactuals, intervention, statistical questions very, very easily. So once you start to connect parameters together, or you're going to find there's going to be a lot of relationship. So let's go through a few of these. If you have, let's say, x, z, and y, this is what we call when x goes to z, z goes to y. This is what we call a mediator, which means that x causally affects y through z. So x causes z, z causes y, which means x also causes y. We could also have moderators if you change the size or direction between the variables. A much more common one is what we call confounders. And confounders are something like this. Basically, when we have two parameters and their cause is one. So one parameter or one input causes two different or has two effects. This becomes a problematic because now if you think about the example of bridges and or of buildings and PhDs, maybe there's a confounder there. We don't know. We're going to have to figure it out. And finally, we have a collider. And the colliders are usually easy to see. So this is when two parameters cause one. So this is a collider. Now you can easily see that a collider is basically an inverse of one of the legs of a confound. So the goal from a machine learning model at this point is we're trying to figure out the relationships between these parameters. And the machine learning model is going to try to figure out, is this going to be a collider? Is this going to be a confounder? Is it going to be like a fork, a moderator? How is it going to feel? What is it going to be? And to answer these, we have a lot of assumptions and math there to establish causality. Markov assumption, deseparation, causal faithfulness, and causal sufficiency. And all of these, I usually keep them in the for the grad class. Actually, we go through these. So once we discover those relationships using these assumptions plus other assumptions, our lives become a little bit easier because now we can have a causal model, and we can use the causal model to infer a causal problem. And this is where we're going to have to do a little bit of practice. So there is a software called Tetrad. Let me show you how to get the Tetrad. It's an open access software actually, so you can easily have it. Yep. So if you go to Carnegie Mellon University, it's been made there. So once you go to Tetrad, or the Tetrad project's been funded by a number of funding agencies, great people working on this project. If you go to visit the website, you can come here, and then you can have it in application-wise. I think it's in Java. You can have it in Python. You can have it in R. You can have a lot of FAQs, documentations, details, and such. And once you have it, it's going to be something like the following. Let's see. There we go. So this is the interface. And all what we really need is the following. So the way to use it, I'm going to show a very brief example. So we start with data. We load the data. Let's see. Let's be, I believe, a text file. We have there. No, I don't want to use this data. My bad. I think, yeah, the one I need is the one for this chapter. There we go, example. Yeah. So we have Z and we have Fy and we have the moment. Validate, load. There we go. So we have it there. And then we're gonna have to, let's see, come up with a graph. We need to search first. So we need to search, assign, and then here is gonna ask you, well, what kind of algorithms would you like to use? What kind of causal algorithms would you like to use? Well, we're gonna go with a very easy one. We're gonna go with the PC algorithm. As you can see, it's made by Sprice, Gilmore in 1990. There's a little bit of description here. And we can set the parameters. You can leave the default ones for now. You can run and search. So you can easily see that F, Y, and Z somehow connect at M. If you look closely, you can see that we don't have any errors. So we don't know if this is going to be a collider relationship, confounder relationship, what it is. So what you could do is you can always go back and try to manipulate these parameters a little bit or choose a different algorithm and see what we can have it. Okay, again, same process. You can also see it here. So this basically tells us we need a little bit more information to figure out the problem. We're gonna have to change some of those parameters a little bit. Let me see, let's try something. So here, if you want to discover colliders, collider conflict, we can have them. What's a very easy way that we can do this? Let's do 3. Let's try. There we go. So now you can see that by manipulating the settings a little bit from the default ones, you can see that Fy and Z causes M, which means if you multiply Fy and Z, you're basically getting at M. Now what happens if you change this back to, let's say, 2? There you go. Now undefined again. Put this as 1. There we go. We have a winner here. But as you can see here, the interesting thing is the following. We already know this relationship because we know the phenomena, but for a different phenomena that we don't know its relationship, sometimes we could get stuck, right? Because we can't really tell what setting do we have to try, what do we have to do. And the goal from this exercise is not really just to cherry pick a specific setting or not. I'm just trying to show you that how even for causal models, it could be tricky because we don't really know, especially if you don't know what causes what. We can't really tell. We're just comfortable with this because we already know that this is the real relationship. However, if you have a phenomenon that you don't know the relation between the parameters, it becomes extremely complex, and all these settings now play a different role. So when somebody says, well, we're using a causal model, that doesn't really mean that the algorithm was able to somehow miraculously figure out the relationship right away from the data. There's a lot of things that could go on before we go into the actual causal analysis. Usually I do this for my class, just a very brief case study. I don't want to use any of the other options for them for now. For grad students, we go a little bit much more in depth. And it's just a little bit easier for, I guess, delivery-wise, to start with something very, very simple and keep the focus of the course on ML, but still show that there is actually something we call causality, causal difference, causal inference, and how we could use it for simple problems. It's always good to try, but once if we're doing like a thesis or writing publications and stuff, then maybe you want to read a little bit more about those causality algorithms. So this is where where we go now to the book a little bit. And I want to cover a few things I didn't get to cover in the slides. I know this chapter can be interesting for many, but I just don't want to lose the notion that it's important to know. I'm not really expecting anybody to be a causal inference expert like from one chapter, but it's just a good stepping stone to learn. So a DGB is simply define the process that generates the data, what causes the data, how the data is being generated from nature, and stuff like that. Let's see what else. Revisiting, we've done this. Oh, yeah, Jasmine always very optimistic. She's great. Those are the questions. Those are questions we had. And what I like about this, like personally, and even if you're a faculty member or a student, you might like want to be starting to ask those philosophical questions. Because in engineering, there's a big component uh, that seems to be um, given for granted. Like sometimes you're just given an equation or building code provision and expected to, know that this is how things work out. But evidently, it may not be the case because there is a lot of it that comes from back. Yeah, 8.1 is interesting because it shows different ways that we can think about causality. This may not necessarily be in engineering. It has a lot of social sciences as well, so this might be a very short, good read that summarizes a lot of the things we talked about. Yeah, we have those. Scroll talked about these. Oh, yeah, this is a good example too. So whenever we deal with machine learning, there's going to be a big component on marginal dependence, which means you have two factors and, we're trying to find the relationship between these two. When we think about causality, we'll start to think about conditional independence. So basically, this is the same data for concrete columns. X is loading, Y is strength, and I'm having the same parameters, loading and strength, but I'm highlighting the data based on spawning or no spawning. So I'm adding a third parameter. So think X, Y, Z. And now, if you look here, first at the top diagram, you can see some form of relationship. Let's see, towards the second bottom half of the diagram. Once you add spawning, now the relationship is a little bit different because you have cases up there, you have most of the spawning up. Even at the bottom, when you have low strength, you have specimen that spawns and specimen that don't spawn. So the relationship with the inclusion of a third parameter becomes a little bit complex. And this is a simple case because we really have three parameters. Imagine if this was an 8-parameter problem or 10-parameter problem or even more, right? So the more you think about this, the more it becomes, okay, well, now I know why ML can work for certain problems and why when I use it, I have to be careful. Same thing with DAGs. You could have very simple DAGs. This is basically how we use machine learning. We have parameter x1, 2, 3, 4. All of them we think influence y. In real life, one could influence two. 2, 1, 4 has a hidden parameter that we can't measure or we don't know about. One also affects 3, and 3 and 2 directly affects y, where 1 doesn't really affect y. So you can see there is a missing link here because could be a realistic causal relationship. This is more of a machine learning relationship where we have to assign the roles. Or even worse, this could be like a linear regression problem where we know x1 plus x2 plus x3 plus x4 equals y. So main difference, big difference. Of course, there's going to be a lot on the do calculus. We don't touch upon this a lot, but this is like a mathematical way to figure out interventions, counterfactuals. There is going to be a lot of footnotes in this chapter because there's going to always be a lot of questions on causality. We also have SEMs, the social equation models. You might be able to think about those in a little bit. Yeah. This was good. So if we think about a mediator, this will be a good example. So if we think about a mediator, this means X causes Z and Z causes Y. An example would be we have fire. Fire is X. Fire generates heat. Heat is Z. Z degrades properties. That's Y. So Z here is a mediator. If you think about a moderator, will moderators change the size or direction of the relationship? For instance, deformation Y in a given structural member can be amplified because of fire. So in this case, we have level of loading, X, deformation, Y, influence of fire, Z. So basically, Z could amplify Y because Z could be lower. You have too much fire, too little fire, too long of a fire, too short of a fire. Could amplify, change the direction and size. Confounder is also another example here. I think 69, yeah, here. So this would be something interesting. Let's go through this example. So seismically active regions, let's call them Z, witness low structural failure. Okay? So if you have a seismic region that's active, it can also have less or low structural failures than other regions with a lower number of structures than Y. Or so we have a different region has a lot of structures, but it has more failures. Well, a very simple solution would be, or a description would be the following. There's going to be some confounder because we have building codes. If you have a building code would say in seismically active regions, you have to use this much detailing, which you don't really have to use in a different region because it's not seismically active, which means the structures in seismically active areas could be a little bit more robust to earthquake loads, seismic loads. So the confounder would be in the case of, common effect or let's say building code. We also have other examples here too for colliders. Yeah, we've seen those assumptions. Yeah, this is where we talk about the causal Markov assumptions, deseparation, faithfulness, efficiency, domain knowledge. This is what we know. Yeah, that could have different shapes. So a skeleton is basically a DAG without any arrows. Then we have DAGs with some arrows, or CB DAGs. Then we have DAGs, and then we have equivalent DAGs, and we have other types of relationship. So for instance, mags and pags and assumed. It might take a while to. I'm really hoping one day I'm gonna have like a full lecture or a full course on causal inference and causal discovery. I just need to hopefully get the time and material put together. Of course, we have a lot of packages for causal discovery, causal Nix, PC, Learn, etc. All of these you can access them easily and use them for Python. We also have something similar for R. We have specific metrics for causality. So causal algorithms have specific metrics and performance indices than traditional machine learning metrics. Yeah, we have also packages for causal inference. And here we have examples, and most of these examples are done. I have a few in Tetrad, so this is the one that we did. But I also have a few towards the end let's see this one here. So this is a much more complex problem. Instead of just Fy times Z, you can see here we have multiple parameters. And the relationships tend to go all the way because in this case, SB is actually the target. And you can see that SB causes, which in reality it doesn't because SB is the target, is the Y. So you can see that some iterations, it may not make sense. Other iterations, it could work out. So you're gonna have to spend a little bit of time and trying to figure out how to make things work. This is why I'm trying to avoid these and in this recording. So now if you rerun the analysis, you can see that okay, C and B now causes SB. All these three parameters do not have as strong of a relationship with that to SB. Then you try again. Well, now C, B, and F, and you continue on trying. And eventually you're gonna come back to causal Nix, and you're gonna see, well, you know what? Once you start to code yourself, this is where coding becomes interesting. And you have the codes there. You have them also online, so you can try those. Once you have the codes up there, and this is actually my co-author Ibiki was actually helping me with this. She's great. You can try those, and you would see, yeah, something like this where things become they start complex and then they loosen up a little bit and then they loosen up much more and then eventually you're gonna come to a DGB that you feel comfortable with or something that could start a new process. I also have an example for the potential outcome approach here, simple example. And you can also see how we can do the do math, the do calculus. let me go back from the top here. For example 5, if you'd like, you need to pause the screen and read this. I mean, to pause the recording and read this. That might help out a little bit. I think it's a good example, but I see myself more inclined to DAGs versus PO just because of the graphical interface kind of thing. And I think in this one, yeah, I remember. In this one, we actually solved it twice. We solved it using DAGs and we solved it using the PO approach. So this would be a nice example to go through. And I have seen this in a different, I think in one of Judah's exercises. Conclusions, definitions. Yeah, these are interesting too. Usually, if in my grad courses, I have these in one of the some portion. I mean, some version of them, like in my exams. I usually in my exams, so I have like a theory part and I have a problem part. For ML, I have like a practice part, so a little bit of theory, 20%, and 80% on problems versus and creating models. So this is how I usually structure my exams for this course. Yeah, you can see there's going to be some very old references here because the philosophy goes back way back than what we do. Of course, Henry Burton in UCLA is a good friend. He also does causal inference papers too. He's great. Yeah, Joda. That's great as well. And that's chapter 9. Okay. We're getting there, guys. I know I'm hoping I didn't need a rush through this chapter, but I'm just trying to avoid having like too many complexities whenever you describe something new. I think ML by itself is something that we have to take, seriously and slowly. Causal inferences, we're gonna get there soon. And I think we should keep the highlight now on machine learning, and then just know that there is something what we call causality that could help us creating better models in the near future. I'm sorry, in the near future. So until I see you again, please stay in touch, and hopefully I'll be hearing from you. Be careful and take care.